Hi, pre-calculus. Today we are going to talk about geometric series. So an arithmetic series, when you add the terms of an arithmetic sequence, a geometric series is when you add the terms of a geometric sequence. When we talked about arithmetic series, we came up with that rule for, finding the sum. We noticed those pairs, right, that added up to be the first term and the last term, and then we knew we had half as many pairs, so we took the number of terms divided by 2. So we're going to do something sort of along the same lines where we're going to develop a pattern that we're going to be able to extend into a formula. So for this first one, it says Austin is looking for an efficient method to compute the sum of this geometric series. So he doesn't want to just put it into his calculator. He wants to come up with some method that he's going to be able to use for any geometric series. So we're going to start with this one. So what we're going to do is we're going to notice what the multiplier is. So to get from here to here, from here to here, from here to here, from here to here, it's always times 4. So what we're going to do is we're going to figure out what 4s is equal to. So all of these are going to be multiplied by 4. So I'd have 4 plus 16 plus 64 plus, so every single one of these I'm going to multiply by 4. That's where I'm getting all of these from, every single thing, times 4, and then just writing it out. So 64, 16, 64, 256, 1,024, 4,096, and then 16,384. Okay. And then below it, I'm just going to write my original sequence. Now, if you look at 1218 in the book, it really steps you through this process and where it all came from, but I'm just going to kind of get right into getting our final answer. Okay, so then what we're going to do is we're going to subtract the original series from the 4 times the series. So when I subtract, notice you have these pair up, 4 minus 4 is 0, 16, like all of these here end up canceling out. And so when you do 4s minus, this is 1s, what you end up with is just this 16,384, which remember came from doing our last term times 4, and then we're subtracting that 1. And so then to figure out what our sum is, 4s minus 1s, that's equal to 3s. And if I subtract these, 16,383, then I can divide by 3, and then that's going to give us the sum of the series. Okay, so the first thing I did was I figured out what the multiplier was, and I multiplied every single term by that, and I wrote it as like 4s is equal to that. Then I subtracted my original series from that quadrupled series, and I got all these to cancel kind of in the middle. So I was left with my last term minus my first term, and then I had to divide by the 4s minus the 1s, so I had to divide by 3, and then that gave me my sum. And so now what we're going to do is we're going to try that same method on this next one. So the first thing we're going to do is we're going to look at this and say, okay, well, what is the multiplier? Multiplying by 6. And here I don't know how many terms there are. In this case, I cannot just put it into my calculator like I theoretically could have done on the last one. So what I'm going to do is I'm going to multiply everything by 6. So I'd have 6 plus 36 plus 216 plus blah, 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 plus whatever 7,776 times 6 is. Okay. And you could put that in your calculator and figure it out. To be honest, I just kind of write it. All right. And then I'm going to rewrite my original sequence below. Oops, I have another set. There should be another 7 in there. And then what I'm going to do is I'm going to subtract. When I subtract, it's always going to be that all this middle stuff is gone. And so I'm left with 6x minus 1s, which is 5s. I know sometimes my 5s and s's look the same. That's really supposed to be the number 5. I don't know if that helped or not. All right, and then what I'm going to be left with is my last term minus my first term, which in the last couple have both been 1. They will not always be 1. And then I'm going to figure out what that is, and I'm going to divide by 5. So I can just put that into my calculator and get my sum. So 9,331. So in general, if I have any series, it's what I'm always doing. It's my last term times the multiplier, right? Minus my first term. And then I divide by the difference between the multiplier and 1, right? Because it's always minus 1s. So it's always 1 less than whatever your multiplier is, what you're dividing by. Okay, so number 20 asks, okay, well, does this work if we had an alternating series? So if we had this 1 minus 3 plus 9 minus 27 plus 81 minus 243 plus 720. I'm just going to rewrite the whole thing, minus 2187. So in this case, the multiplier is I'm multiplying every time by -3. So if this is equal to s, okay, then we're going to figure out what -3s is. So -3 plus 9 minus 27 plus 81. And then it would be minus 27 plus 81 minus 243 plus 729 minus 2187 plus, then it would be 3 times 2187, which is 6,581. All right, so I have all that, and then I'm going to subtract, right? So when I subtract -3 minus a -3, that's -3 plus 3. 9 minus 9, 27 minus -27. Okay, again, these all cancel. And again, I'm left with my last term minus my first term. And now be careful, I have 3s minus s, that's -4s. So I'll be dividing by -4. So it's always my multiplier minus 1. And then you end up with -1640, which would be the same thing if you added it up. So it works even if you have a negative multiplier. Okay, so just like yesterday, after we sort of started seeing, okay, it's always the same process every single time, what we want to do is we want to come up with a formula to generalize the process. So it says, let's say we have this s sub n equals this. So the a, this is like our first term every time. The a sub, I always write it as a sub 1. Okay, so if I have my s sub n is the first term plus my first term times r. So my multiplier is r. And then to get my next term, I take my last term and I multiply by another r. So it's my first term times r to the second. My first term, I multiply by another r times r to the third. And so on to a sub 1 times r to the n minus 1 power. Remember, this was the rule we had to find the nth term of a geometric sequence. Okay, so my multiplier in each case, it's r. So then I'm going to do r times s sub n. So if I do this times r, I would get a sub 1 times r. If I do this times r, I get a sub 1 times r squared. So it's the same thing as before, right? I'm going to multiply everything by r. To get my last term, I take this last term and then times r. And then we're going to subtract. And when I subtract, I get rid of all this stuff. I'm left with this minus this, and then I'm going to divide by the difference. So this is r times s sub n minus s sub n, right? Or basically r minus 1. Okay. So here, before I bring this down, I can simplify, right? If I have r to the n minus 1 times r to the first, remember you can add the exponents. So I have a sub 1 times r to the n minus a sub 1 all over what I would have to divide by to get, see how these both have an s sub n in them? It's like s sub n times r minus 1, right? So what I have to divide by here is r minus 1. So the sum is right here. Now, a lot of times when you see the rule, you won't see it written like this. What you'll see is, oh, there's a greatest common factor here. I'm going to pull that out front, be left with r to the n minus 1. Right? If I distribute this back in, I end up with this. A sub 1 times r to the nth is this. A sub 1 times 1 is this. All over r minus 1. Now, it's not important that you can derive the formula. Okay, if just do you buy it? Do you buy that we followed those same steps and that this is what I end up with in general? So you'll see this sometimes for the rule. The other thing you'll see is that, like, if I multiply the top and the bottom by -1, you'll also see it written as a sub 1 times 1 minus r to the n all over 1 minus r. And that is what you see on your math note that you have in your notebook, is that rule right there. And so what we're going to do next is we're going to practice using this rule to do a couple more. So this actually comes from the homework. It says use Austin's method to compute the sum of each series below. Now, I would use this rule for part A, but I actually wouldn't use it for part B because I don't know how many terms there are. I could solve to figure it out, but it's not like a super quick solve. And so I would actually use Austin's rule for that one. Okay, but for the first one, I can use this rule. So for part A, I know my first term is 1. I know to get from one term to the next that my multiplier is 5, so times 5. So sometimes when we were writing the geometric rules, we use, a times b to the n. That's what we use when we talk about exponential situations. Sometimes you'll also see r, like in this formula here. So I know that r is 5. And I know I have 1, 2, 3, 4, 5, 6, 7 terms. So n is 7. So in this rule, to find the sum of those 7 terms, I would do 1 times 1 minus 5 to the 7th power all over 1 minus 5. And then you could just put this into your calculator all in one step. And to be honest, I really do put it into my calculator all in one step. I don't, mess around with, okay, I have to first do, I have it in here from before. First, I need to figure out what 5 to the 7th is, and then I have to do 1 minus 5 to the 7th and figure out that is, and then I have to divide. Like, if you just put it all in one step, then it less likely you're going to make a mistake. If you're in Desmos, use the fraction bar. If you're using an Inspire control divide, will get you the horizontal fraction bar. Okay, so you put that all in. And then I had the answer on the screen. What did I have? 19,531. Now, the reason I wouldn't use this for part B, I do know the first term. I know the multiplier is 3, but I don't know how many terms are in there. So for part B, you've got a couple of different ways you could go. You could say, oh, I really want to use that rule. And then to do that, I have to figure out what n is. And so what I would do is I would say, okay, I know things that are geometric. The rule is a sub 1 times b to the n minus 1 power. And I know my first term is 5. And I know my multiplier is 3. I want to know what n value will give me a last term of 885,735. Okay? So you could do that and you could solve and divide by 5. Then you get 3 to the n minus 1 equals whatever that is. And then you have to take the log base 3 of both sides, right? Get your n minus 1 equals and then add. You could do that and use this formula. But really, what I think is a lot easier for this one really is to use Austin's method. Sometimes, even though it might seem like, oh, a formula is always the way to go, in this case, I don't know, I don't think it necessarily is. Okay, so we said that our multiplier was 3. So then I would figure out what 3s is. So, and you might be getting to the point where, like, do I really have to write this all out? I know that these are all going to be the same. And what I really care about is just that this last term is getting multiplied by 3, because when I subtract, everything else goes away. So what I'm really interested in is my last term minus my first term. So here's one we're seeing. It's not always minus 1. It's minus the first term divided by the difference between your multiplier and 1. 3s minus 1s is 2s. So divided by 2. And then just, again, put that into your calculator, and I would put it into my calculator all in one shot, and you get 1,328,600. Okay, so that's the big idea, geometric series.